Good morning, everyone. I'm Vivian from Singapore Water Association. Welcome all to today's webinar on the biofilms in the urban water cycle. Today's session is co-organized by Singapore Water Association, Singapore Centre for Environmental Life Sciences Engineering, and the Singapore National Biofilm Consortium. Before we proceed, I'd like to touch on some housekeeping rules and disclaimer clauses. To ensure the session to be smooth, please mute your microphone and turn off the camera. You may communicate with us after the session. Please share your questions in the chat, where we'll try to provide answers where possible in the Q&A segment. Do identify yourself so we can respond to any unanswered questions after the webinar. We'll be recording this session and reserve the rights to the video. Please complete a post-event survey, which upon return, will forward the recording and presentation text to the respondents. All information in this webinar is for general information only and does not contain or convey any legal advice or administrative assistance. Information shared today is true and accurate as of publication date. SWA and SMBC reserve all rights in the provided materials. Today, we are pleased to have Professor Stefan Gelabert, Center Director of SCELSE and Director of SMBC, Dr. Lau Ying-Yun, Program Manager of SMBC, Dr. Amit Kumar, Co-founder and CEO of Biopsin Private Limited, and Mr. Andy Vajawan, Director of United Water Technologies Private Limited, to share with us today. For today's webinar, we'll start off with a welcome address by Singapore Water Association Vice President Finance, Mr. Charles Quek, and the speakers will further advise us on the role of biofilms in the urban water cycle, what is the impact of biofilms, and what can be done to improve detection and water treatment quality. Without further ado, may I now invite Mr. Charles Quek, Singapore Water Association Vice President Finance and CEO of HSL Constructor Private Limited, to give us the welcome address. Mr. Charles, please.
Thank you, Vivian. And Professor Stefan, Dr. Lau Ying-Yun, Dr. Amit Kumar, Mr. Andy Vajawan, ladies and gentlemen, a very good morning to all of you. It gives me great pleasure to welcome all to today's webinar jointly organized by the Singapore Water Association, Singapore Centre for Environmental Life Sciences Engineering, and Singapore National Biofilms Consortium. The impact of the COVID-19 pandemic is far-reaching and much deeper than many of us could have expected just 7 months ago. But the quality of drinking water should never be compromised by the pandemic, and in fact, we should now be even more concerned to the role of biofilms in our Singapore's urban water cycle. We are honored this morning to have expert speakers from the bio-life sciences and biofilms engineering to advise us on such an influence to our daily lives. We hope to create new collaborations between key stakeholders, increase Singapore's competitiveness, add value and resilience to both the water and biofilms environments. It is therefore timely that SWA, SCE, LSE, and SMBC to step up support to organize such a webinar to address the impact and role of biofilms, as well as what can be done to improve detection and water treatment quality. Singapore Water Association has been instrumental in providing a platform to build effective networking, facilitate opportunities for collaboration, and foster the exchange of ideas and knowledge amongst member companies. SWA also serves as an integral linkage for members to the global water network through the setting up of Singapore's pavilions at overseas trade shows, overseas missions, and business seminars. When SWA started in 2004, our mission was to develop a vibrant and dynamic Singapore water industry with a vision to be the regional hub for all water services and technologies. Our current 260 members now comprise a diverse mix of both local and international organizations, commercial companies, research institutions, conglomerates, SMEs, and even individuals, providing expertise across the whole water value chain to create this vibrant water scene in Singapore and beyond. Together with the policymakers, all of us have played and will continue to play a vital role in solidifying Singapore's status as a model for integrated water management, an emerging global hydro hub, and a leader in the water revolution. COVID-19 is significantly impacting our health, lifestyle, business, and the economy. As a society and businesses race to reopen, the pandemic has brought fast-moving and unexpected variables. Notwithstanding any variable, the quality of water cannot be compromised, as it endangers our health and the whole ecosystem encompassing households, agriculture, industry, energy, and the environment. Hygiene, sanitation, and supply of clean drinking water affects everyone on the other hand. The world's supply of fresh water is depleting, and it is estimated that 2/3 of the world's population will encounter water shortages by 2025, given the current consumption rate and increasing population growth. With more than 2/3 of global population in Asia, the pandemic has shown how tightly the Asian market is driven into the economic and social composition of the world with our display of swift reaction, steadfast policies, and innovations. Locally, Singapore Water Association is working closely with businesses to help mobilize, stabilize, and resume operations with our SG United updates, SW Assist, SW Watch, initiatives, and weekly updates on our website to ease our members' woes with the current economic uncertainties. SWA is also working with the Singapore Business Federation, Employment and Employability Institute, Enterprise Singapore, Skills Future Singapore, and several partners in assisting local companies for some retraining and job placement implementations. In April, we have also launched the SWA Marketplace Assist platform for our SWA members to step up or seek help from fellow members or partners. The aim is to facilitate business continuity within the SWA community and to tide over the challenges arising during these difficult times and disruptions to the value supply chain. By innovating and generating such collaborations, we also enable ourselves to move up the value chain to be leaders, partners, and advisors to businesses and communities in the water cluster. In closing, I look forward to hear some of the knowledge shared and hope that our members will take advantage of this session not only to seize business opportunities, but also to contribute to the region's overall research and response to the technology development of a better treated water cycle. Thank you, all of you.
Thank you, Mr. Craig. May we now invite Professor Stephen Kilibert, Center Director of SCELSE and Director of SMBC, to give us an introduction of the two centers. Professor Stephen, please.
I hear you. Oh, you can hear me. Thank you so much. We had some initial problems here. Very sorry for that. Thank you so much for the invitation to talk and the very informative introduction given by the chairman. So I'd like to just give you sort of a brief introduction to the two biofilm centers or biofilm organizations as they are, SCELSE and SMBC. And SCELSE, the Singapore Centre for Environmental Life Sciences Engineering, is an RCE, which is a Research Centre of Excellence, that is funded by the National Research Foundation and the Ministry of Education. And it's hosted by two universities, by NTU and NUS. And the research that the centre conducts, so it's life sciences engineering research, is addressing clearly what is a growing need for understanding the biology of microbial biofilms and microbiomes in all systems. So the mission for SCELSE is what you see here on the slide. It is to discover, control, and direct the behavior of microbial biofilm communities and microbiomes for sustainable environmental, engineering, public health, and medical applications. And the reason it can do so and it can operate across these seemingly diverse range of domains and areas is the commonality of biofilm communities and microbiomes. So the biology has commonality in that system across these different application areas. So to address that mission that SCELSE then has, we are taking advantage of expertise that we have built by the different research clusters in the organization of SCELSE. And they cover, as you see here, from environmental engineering to metagenomics and microbiomes, to that of understanding the biology of microbial biofilms, and public health and medical biofilms. And these are underpinned by an integrative analysis unit that we have in SCELSE across the two universities for providing expertise in experimental design and massive data handling and analysis. The systems that we are operating on are often very complex, and as you understand, the members in biofilms, the microbial members, can be highly diverse and in the order of hundreds of thousands of different species, and it's the function of those that we need to understand in order to understand biofilms and in order to either take advantage of biofilms or to remove biofilms when they are not wanted. The research then is conducted in particular core or integrated research themes. And here are the main such integrated research themes across the clusters that we have in place. And just to give you an idea of what we do, so you can sort of understand the scope and the activities and expertise in SCELSE. We deal with the urban water cycle and all aspects, in fact, of the urban water cycle, from the treatment phase to distribution of the water. We are engaged in large-scale air microbiome research, and that is obviously very important and timely now with the pandemic. And it's particularly important, of course, in the public health setting in an urban ecosystem. We are part of a national marine science program where we contribute expertise and R&D on marine biofilms and microbiomes in different parts of that ecosystem. Host microbiome interactions are very important. We call them holobionts. So that is the combined biology of the host and the microbiomes. So highly diverse microbial communities. Very important for humans, obviously. You know that your gut microbiome needs to be in order for you to sort of perform well. But it also applies to all systems, all organisms. We have a focus on developing systems for understanding biofilms, so experimental biofilm communities are set up. So we understand the complexity in these often highly diverse systems. It's not just a matter of studying one species, one organism. It's often the case in traditional microbiology. This is studying the entirety of the community. And there's an emphasis on the biofilm matrix, and that's the house that the microorganisms use. They build the house to form a biofilm. So the matrix is an important component of establishing resilient biofilms. Also the reason why it's often difficult to eradicate and remove biofilms. So these integrated research themes then, they emerge from the cluster-based research that I spoke to, and they align well with the development of research priorities in Singapore. Indeed, SCELSE is a sort of Singaporean organization, of course. And SCELSE is, so trying to shift back to next slide. There you go, thank you. And SCELSE is well integrated in Singapore. This is an example of that across different organizations. And we play sort of a catalytic role in many of the activities that we have with these partners, from the left-hand side, clinical institutes, to government agencies and other organizations, institutions in the middle, and on the right-hand side, examples of different industry collaborators that we have. And on that basis, the National Research Foundation in Singapore initiated and funded the Singapore National Biofilm Consortium, which is a technology consortium. And it was established early last year. And they did that in order to translate the research findings and the science and the capacities that have been developed by SCELSE. And indeed that makes sense to do so, because biofilms and microbiomes, they do matter, and they have significant implications, particularly as depicted in this slide, financial implications across many market sectors. And just to mention a few of those, if you look at the left-hand side in that circle, it speaks to a range of areas in personal care, food and food safety, health, oil and gas, wastewater treatment, marine, erosion, and industrial biotech. And the number is staggering, the implications, the financial implications per year globally. Those numbers derive from, I should say, from NBIC, which is the National Biofilm Innovation Centre in the UK, another international biofilm centre which we collaborate with. I'll come back to that very shortly. So specific examples, so this sort of makes perhaps sort of a bit more sort of clear and easy to relate to. For example, in cystic fibrosis, respiratory biofilm-based infections, the biofilm is the problem. And the only way of dealing with that issue and to help the patient is to remove the biofilm. And it has a distinct large biofilm burden globally, as you see here, about $4 billion per annum. In the marine industries, marine shipping, biofilm formation or biofouling is clearly a massive burden financially globally. For other infections where biofilms are important or key, include urinary tract infections. It also has a sort of a very large global cost, and the one that sort of is at the peak of this issue of needs to understand and deal with is biofilms that are causing food poisoning, with a staggering global burden per annum. Thank you. So the Biofilm Consortium, then the National Biofilm Consortium, this technology consortium that was introduced by NRF, its mission and vision then on that basis is to foster interactions, establish close collaborations among IHLs, so different universities, research institutes, government agencies, and industry in Singapore, and in particular being hosted by SCELSE to leverage on the expertise that SCELSE has built, which is multidisciplinary, and then deliver scientific and translational outcomes on that basis. So the structure of SMBC is such that it's funded by NRF, as I mentioned. The funding drives industry and IHL partnerships, technology adoption and translation. Currently, the host institutions are NTU and US. The IHLs, the academic partnerships, can be beyond the NTU and NUS, and we welcome other such universities and IHLs to be part and engage in this organization and drive development of applications based on understanding biofilms. The research lead is SCELSE, and the administrative unit is that of the Tech Transfer Office at NTU, which is Intuitive. We have a global partner, which is the National Biofilms Innovation Centre that I mentioned. They have good experience in driving research between universities and industry. In fact, they have in the order of 200 member industries, and have the experience and expertise that are very useful for SMBC as its funding its way forward and best practice. Membership categories are of different kinds. So industry obviously are members of SMBC, but it can also be principal investigators or researchers and institutions more broadly. And that definition, as you see here, is broad, including agencies, associations, platforms, etc. We welcome as members, and indeed we have several such members. So SMBC then has 4 main sort of collaboration focus areas to define its activity, and that's perhaps useful just to mention those if you're interested and you want to know the scope of SMBC. So one is microbiome engineering, when we can manipulate in different ways or establish a novel bacterial community in a particular site for functional applications. Monitoring is important, and environmental monitoring is developing quickly. And in fact, there are different types of monitoring, and you will hear one such today in a presentation this morning on real-time detection sensors. we have a large toolbox and technologies that we make available, and that is important for a proper assessment framework. And as I alluded to, these systems are complex, highly diverse often, so it's important to have high resolution assessment capacity for microbiomes. And based on that knowledge that we develop in these areas, we aim for developing better clean surface technologies, and that can include designing surfaces so that they clearly allow for either removal or augmenting material colonization, directly changing the surface, or adding bioactive, for example, particular molecules to modify a biofilm that is already established on that surface. For the governance and organization of SMBC, importantly to highlight is that we have not just a technology management committee and an industry advisory board, which are very important that we do have. We also have industry liaison officers for the different areas that have been identified in discussions with industry to be particularly important and where there's a need when we establish collaborative research. So these industry liaison officers are researchers, as research fellows who have expertise in these areas. So, for example, high throughput sequencing, microscopy imaging, and bioprocess engineering are tools, technologies that are very important to apply often. So our surface technologies that span from physics, chemistry to the life sciences, or the interfaces between those. And emerging is a need for expertise in plant and soil microbiomes, understanding the urban and built environment, so we can deal with many of the public health issues in a built environment where microbiomes and biofilms are key or problems, and human microbiomes and other holobiome systems. In the office, Michelle Birnbaum is in charge of business development. Ingu Law is the program manager, and Smitha Sunildip is manager and handling specific projects and operations. So just to give you then an idea of what are the areas that we are now engaged in, and what is the interest and who are the members, and just to sort of run you through it very quickly. We're currently focusing on, or have these areas established in water, with then different members, companies and associations, in biomedical healthcare and cosmetics, and an area that is now emerging and is becoming important is that of agri and aqua culture technologies, because of Singapore 30 by 30 into the food sector. There's also obviously important that we have, as I mentioned, we can provide information expertise on various technologies in analytics, for high resolution analytics. That includes, for example, imaging, biomes. Surface technologies matter also, and the last two domains then are food and beverage, and oil and gas, where we have interest members and research collaborations. So for the members, we provide different kinds of support and activities. So we provide funding for specific projects, often projects that would run in the order of half a year, perhaps a bit longer, where we provide cash as seed funding, $50,000, and that is often then met by a industry member or partner, either by cash or in kind. We also advise on collaborative grants and larger scale opportunities as we go forward. We provide expertise broadly and consultancy, and we truly have world-class facilities required for doing research in these areas and equipment that becomes available to members. Also trying to sort of provide know-how where there's an interest and where there's a need, and where we discover there's something that we want to communicate, by tailored courses, running seminars and workshops, and we do that locally, but also by engaging international experts. And we do that because of our international collaboration that I mentioned, where we have sort of a global biofilm network, both for academic and for industry R&D. And this is my final slide, just to highlight that. So SCELSE is one of 4 international biofilm centres. I mentioned the National Biofilm Innovation Centre in the UK, but also in this alliance and collaboration is included the Centre for Biofilm Engineering in the US, which is focusing mainly on industry. They have about 30 large industry members and they do industry research in the main. And the Consortium Biofilm Center in Denmark is focusing on medical and biomedical biofilms. So they're very complementary in that respect. So sharing of information across these have been invaluable. So it's my last slide, and I thank you for your attention, and I will hand back over then to Vivian. Thank you.
Hear me now?
Yes.
Thank you, Professor Stefan, for your invaluable sharings. May we now invite Dr. Lau Ying, Program Manager of SMBC, to give us an overview on the role of biofilms in the urban water cycle. Dr. Lau, please.
Thank you, Vivian, for the introduction. This morning, I'll be talking a little bit on examples of role of biofilms in the overall urban water cycle. So whenever I introduce the Singapore National Biofilm Consortium, I'm always asked the question of what exactly are biofilms. So biofilms can be defined as aggregates of microorganisms, in which cells are embedded in a matrix of self-produced extrapolymeric substance, which allows them to either stick to one another or onto a surface. So biofilms can be divided, or the life cycle can be divided into 3 stages, starting with the attachment of free-floating planktonic cells, which then starts to produce EPS, extrapolymeric substance. And the production of EPS allows the emerging community to develop a complex 3-dimensional structure. So as the biofilm mature, it then goes into the 3rd stage, which is the detachment stage, of which small or large clumps of cells will dislodge from the biofilm and disperses individual cells to colonize new surfaces downstream from the original biofilm. So biofilm is the most widespread or successful mode of life on Earth. It drives many important biogeochemical cycling of elements in natural systems. It plays a very important role in engineered systems, as well as it has impact on higher organisms such as human colonizing our system, and has significant impact on its health and medical applications. So before going into the examples of how biofilm can interfere with the urban water cycle, let's take a look at the urban water cycle here in Singapore, which I'm sure a lot of you are very familiar with. So starting from the discharge of water from residential and commercial premises, used water are being transported to used water treatment plant through the sewer network system. So in used water treatment plant, the main purpose here is to achieve nutrient removal, mainly in the form of nitrogen, phosphorus, and organic carbon, using activated sludge treatment process. The used water is then separated from the sludge, and either is discharged to receiving water bodies or circulated to new water treatment in Singapore, in which case it will go through microfiltration, ultrafiltration, reverse osmosis, and UV disinfection. So the treated or new water can directly be used for non-potable purposes, such as for industrial purposes and cooling towers. And today, Andy from United Water will be talking a little bit on the technology that they have on offer to monitor biofilms in cooling towers. And new water is also mixed into our drinking water reservoirs for portable reuse. So water is then drawn from the reservoirs and distributed back to residential and commercial premises through the distribution, drinking water distribution and disinfection network. So what is missing here is desalination and imported water, which are also 2 important sources of water in Singapore. So let's take a look at the examples of biofilm in the urban water cycle. So the moment used water enters the sewer network system, it provides substrate or food for biofilm to grow in the sewer pipes. So in rising main sewers, so pipes that are going against gravity, these pipes are actually completely submerged with water, hence creating an environment that's anaerobic. So it can encourage the growth of anaerobic biofilm. So mainly the 2 groups are microorganisms that have an impact on the function or the the integrity of the concrete sewer system are methanogens and sulfate-reducing bacteria. So methanogens can convert the organics in the used water to methane, which is a greenhouse gas, and sulfate-reducing bacteria reduces the sulfate and produces hydrogen sulfide. So as this used water, or as this water transport from rising main down to the gravity sewer, which has a headspace now, the hydrogen sulfide can then diffuse into the gas phase, and aerobic biofilm now in the head can then degrade or convert the hydrogen into sulfuric acid, which then would corrode the headspace of the sewer pipes. So this is particularly important in aging sewer networks. Not so much probably in Singapore, but in countries like Europe and in the US, this could cause severe problems. So a lot of the research has mainly been looking into dosing chemicals that would inhibit sulfate-reducing bacteria, and these chemicals include oxygen and nitrate, which would prevent anaerobic conditions. And continuous effort now has been looking into combining online monitoring and chemical dosing to optimize or reduce the amount of chemical that you use, but maximizing the impact on inhibiting these biofilms. So of course, when we talk about biofilm in urban water cycle, the first thing that comes to mind is biofouling of membranes. And membranes are, of course, used a lot in the overall water and used water treatment process. In new water treatment system, membranes are used all the way from microfiltration down to reverse osmosis to remove a range of contaminants from suspended solids all the way down to bacteria and viruses. In used water treatment, for used water treatment purpose, membranes are used to separate the treated effluent with the sludge to create a much higher quality effluent. So the fouling of membranes, though, would significantly increase the transmembrane pressure, which in turn increases operational cost, of course, because of the increase in use of energy. It would the acidic byproducts that are formed by biofilms can also potentially degrade the membranes, which would eventually result in the need to replace these membrane. So a lot of membrane work is done in NURI, which is a collaborator of SCELSE, and they also have a partner, Singapore Membrane Consortium, which again is a strong collaborator with SMBC. So, so far, a lot of the biofouling control strategies involve pre-treatment of the water, such as the dose of flocculation, even biocidal agents, and of course microfiltration and ultrafiltration. But one of the concerns of dosing biocidal agent is that it could potentially result in the build-up of resistant biofilm. And it's often very difficult to completely get rid of biofouling, since the survival of only a few cells can eventually lead to the colonization of the membrane and propagation. So you can probably delay biofouling, but cannot completely get rid of the growth of biofilm. So you could also clean the biofilm over time, but again, you could never ever get rid of biofouling or biofilm formation. So what we do here in SCELSE a lot is to try to understand the signaling mechanism that would lead to the change of planktonic life form into biofilm life form. And one of the key signal response pathway is a cyclic di-GMP pathway, of which in response to certain external signals, planktonic cells can upregulate the cyclic di-GMP levels, which would bring about a cascade of metabolic changes, resulting in the change from planktonic to biofilm life mode by production of EPS. So again, in response to a different set of signals, cells or the biofilm can then downregulate cyclic di-GMP levels, resulting in dispersal of the biofilm. So reverting back from biofilm life mode all the way to planktonic cells. So one such application that SCELSE has came up with is the use of nitric oxide donor compounds. So nitric oxide has been shown to be a signaling compound that can result in, that can interfere with the cyclic di-GMP pathway. So by treating the fouled or RO membrane that is fouled from biofilm with nitric oxide donor compound, the researchers found that biofilm can be reduced by more than 50% in their biomass on the surface of the RO membrane. So this is, and the analysis of the community of the biofilm also showed that there was no signs of buildup of resistance towards the anode donor compounds. So SCELSE actually holds the IP for cell signaling and dispersion of biofilm in both water and healthcare applications. If you are interested, you can get in touch with me and SMBC. So the other application or important implication of biofilm in the urban water cycle is its impact in the drinking water distribution system. So the existence or the role of biofilm in drinking water is important, as it can alter taste, smell, appearance, and of course the biological stability of the drinking water. And one such example would be the different use of disinfectant in the drinking water distribution system. For example, in Singapore, we use chloramine instead of chlorine, as chloramine actually produces less disinfection byproducts. However, the use of chloramine introduces more free ammonia into the drinking water supply, which could encourage the growth of ammonia oxidizing bacteria in the biofilm. And there are efforts in trying to understand how exactly do these biofilms interfere or affect the quality of drinking water. And this is also something that we do, and we have ongoing studies in SCELSE looking into that. However, to really understand the impact of biofilm on drinking water supply would require an integrated approach from understanding the growth characteristics to the effect of operational conditions, and we require good monitoring and characterization methods to come up with appropriate control practice. So today, Amit from Biopsin will be talking a little bit on the technology that they have on offer to monitor certain pathogens in the drinking water supply. So I've so far mostly talked about how biofilms can bring about negative impact on the urban water cycle. But in certain applications, we also want biofilm to grow. And one of such examples is biofilms in used water treatment systems. So as I mentioned earlier, used water treatment functions to mainly remove nutrients in the form of nitrogen, phosphorus, and organic carbon, because the loading of such nutrients into receiving water bodies can cause eutrophication. So based on our understanding of the nitrogen cycle, we can encourage the growth of certain bacteria. So in this case, we want to convert ammonium all the way to dinitrogen. So we can encourage the growth of ammonia oxidizing bacteria, AOB, with NOB, nitrite oxidizing bacteria, together with heterotrophic denitrifiers. Or in certain systems, we can also encourage the growth of AOB, ammonia oxidizing bacteria, coupled with NMOX for shortcut nitrogen removal. So there are many different configurations of reactors in the market to encourage the growth of these groups of bacteria. And we could also even add different packing material as carriers to encourage biofilm formation on these in the system, so, such as the moving bed bioreactor. So of course, biofilms need not always require a surface. There are also systems that encourage the growth of suspended biofilms, such as granules. As you can see in the slide here, they are round and has a big diameter compared relative to floccular sludge. And granular sludge has an advantage over floccular sludge because they settle a lot quicker, and hence has an impact on the overall footprint of the used water treatment system. So the last example that I'll give is in understanding microbial communities in the waterways. And in Singapore, we have a unique man-made system, of which we are one of the few countries that recover or reclaim stormwater for reuse. And as a consequence of that, we have many reservoirs, mostly man-made, and as many as 8,000 kilometers of waterways and drains to channel stormwater into our reservoirs. through the active and beautiful and clean water. So in SCELSE again, there is a program, a research program that is looking into or understanding the role of these micro-communities in both the water column as well as the water sediment. And we have investigated more than 32 potentially influencing factors that drives the microbial community structure in this man-made environment. And we found that it's only a handful of influencing factors actually form or has an influence in the community structure. This has an implication suggesting that there is a potential to manipulate and the microbial communities to potentially remove certain, to drive them to perform certain functions that will potentially favorable in treatment of these water. So that's probably the end of my talk, and I've given some examples where biofilms can be detrimental to some processes in the water, urban water cycle, but we can also manipulate them or optimize for biotechnological applications. And as mentioned by Prof. Stefan, we don't only look into biofilms in the water cycle, but also in many other sectors. And if you have any further interest or idea for collaboration, please reach out to me or Michelle via our email addresses. And thank you. So back to you, Vivian.
Thank you, Dr. Lau. May we now invite Dr. Amit Kumar, co-founder and CEO of Biopsin Private Limited, to advise us on the rapid and gold pathogen detection. Dr. Kumar, please.
Thank you, Vivian. Can you hear me?
Yes, we can hear you,
Okay,
Dr.
yeah, thank you. So at Biopsin, we are aiming to transform microbial diagnostics by enabling rapid detection of pathogens with gold standard limit of detection. Or in other words, what we are trying to do is that we are making it possible to determine whether a fast-moving consumer product of food or water is safe or contaminated with pathogens before it's released for consumption. And yes, that does not happen right now. And as a result, 1 in 10 people fall ill every year because of exposure to pathogens. And even according to most conservative estimates, its global economic burden is in hundreds of billions of dollars. And this happens primarily because the method we use to detect pathogens today is fundamentally over a century old. It is tedious, it requires trained professionals to do the tests, and it requires a dedicated lab to perform the tests. But that isn't even the real problem. The real problem is that this method or pathogen testing with this method is dangerously time consuming. And considering all factors such as logistics, it may take anywhere from 1 to 2 weeks just to get the result. And you can imagine that most fast-moving consumer products, food and water, can't sit on shelf for that long. So the accepted industry practice right now is to release these products without ascertaining the microbial quality of the product. And relying on the good manufacturing practices and in the hope that microbial testing results would come out fine when they do. But every once in a while, that's not the case. And that is when we have product recalls, disease outbreaks, and even loss of human lives on our hands. So we started Biopsin with the goal to build the world's first solution for rapid detection of pathogens with gold standard limit of detection. So industries can detect pathogens in their products with the same gold standard limit of detection as the conventional method, but almost in real time instead of weeks. And ascertain the microbial quality of the product before they release the product for consumption. We are not there yet, but we are getting closer. Our solution would consist of a cartridge and a device The cartridge consists of a pre-processing unit, which includes a filtration module and a pathogen trapping slide. The entire microbial detection takes place in the cartridge, that is from adding the sample to collecting the waste. The device enables all the processes in the cartridge and also captures, analyzes, and displays data. So to give you a brief idea of what the basic working principle is, we actually separate bacterial cells from the sample or from the bulk matrix of the sample and concentrate it in between a gradient of coarse filters and a microbe rejection filter. And then this bacterial concentrate, which is a purer form that we want to use in the next step. So this bacterial concentrate is passed through a pathogen trapping slide, which traps only the target pathogen or the pathogen that we're interested in detecting. And it traps it with high affinity and selectivity, and everything else is washed away. And then a detector in the device that I showed earlier can instantly identify which pathogen it is. So this is our preliminary result for target bacteria attachment on pathogen trapping slides after it passes through the filtration module. And well, these are two different pathogens. The first column is Staphylococcus aureus and the second column is E. coli. And what we can observe here is that when the sample does not contain the target bacteria, but it contains many other bacteria, nothing attaches to the pathogen trapping slide. And this in itself is a big achievement and was a hard problem to solve. And when there is target bacteria in the sample, well, almost all target bacteria attaches to the pathogen trapping slides along the length of the slide and is detected by detector. And this leads us to conclude that our method can successfully trap bacterial pathogens in a targeted way and identify them. So where we are right now, we have already established a lab-based proof of concept for Staphylococcus aureus, and we are trying to extend this to E. coli, Vibrio, and Legionella now. But at the same time, we are also prototyping to develop the commercial version of the product, the kind of cartridge and device I showed earlier. So microbial testing spans across many industries. It's required in a number of industries, but currently we are focusing on food, water, and fast-moving consumer goods, as we feel that the need is most urgent in this space. As for water, well, the routine bacterial tests include heterotrophic plate count, testing for E. coli, and testing for Legionella. We already have very good results for E. coli, and we will start work on Legionella soon. So to give you some idea about what Biopsin is like and what we do here, we routinely perform microbial testing in food and water by traditional as well as relatively advanced methods. We have a 2,000 square feet lab space, a BSL-2 facility. We are not accredited as a microbial testing lab yet, but we have initiated the process to get accredited. So if you are looking for a solution to any problem in this space, we would love to collaborate. So all of this has been achieved because of the incredible hard work that the team has put in the last year. And I also want to take this opportunity to thank our investors, and a special thanks to Temasek for putting their faith in us and for a very generous grant. So I believe that with increasing incidences of disease outbreaks and the advent of antimicrobial resistance, rapid and accurate detection of pathogens would no longer be an option. It will be a necessity, and I'm very hopeful that we will be able to bring the solution to the market very soon. Thank you. Thank you, Vivian. Back to you.
Thank you, Dr. Ahmed. Last but not least, let us invite Mr. Andy Verjana, Director of United Water Technologies Private Limited, to speak to us on the biofilm sensors, real-time applications, and the benefits of water treatment. Mr. Andy, please.
Thank you very much, Vivian. Hi all, thank you for joining this seminar. Thank you for the organizer to invite me to introduce these excellent products that we have in our store. My background is showing NextGen. NextGen is a company that United Water Technology actually formed to specifically focus in this one core technology, which is basically a real-time biofilm sensor. Next slide, sorry. Yep, so this is just the agenda that what we're going to have a look at today. Next slide. As I mentioned before, NextGen is a subsidiary of United Water Technology. It is formed to solely focus on these three core technology, which is first thing is a real-time online continuous biofilms monitoring. And then second is the ULE, is the ultra low energy aeration system for typically for sewage treatment plant and wastewater treatment plant. And then the one is a nano bubble generation system. Next slide. Yeah. Okay, as Professor Stefan and then Dr. Lau mentioned in their presentations that biofilm touches so many industry, and then unfortunately it does cause various problems and then causing a lot of financial issue as well, from microbiological corrosion, from contamination to many various things. So almost every single industry that we have touches by the impact of the biofilms. Next slide. All right, so this is the focus of my talk, or my I would like to share with you all that there is a way to monitor these biofilms continuously in a real time in an effective manner. So this is a biofilm sensor. It's called Alluvial biofilm sensor. It is a real-time biofilm sensor developed at the Institute of Marine Science in Italy. How it is actually different from other so-called biofilm sensor in the market is measuring the electrochemical signals of biofilm activity. As we install basically the sensor insert into the pipe, any piece of equipment, if there's a big population or there's a population of bacteria in the body of water, and then when it started to form biofilm, it will also start forming biofilm on the tip of the sensor. And then as the film form at the tips of the sensor, it will give electrochemical, and then this sensor will pick up the sensor and give us the continuous or the real-time readings. Because it's measure only the electrochemical signals of the biofilm itself, the activity on the tip of the sensor, it's only measuring the biofilm growth or the biofilm present. It does not measure any other things. There are many other probably so-called biofilm sensor in the market that measure on the electrical conductance, heat transfer efficiency, that probably cannot differentiate between different type of deposit that actually sticking to the sensor itself. Next. So again, it's actually constructed. The sensor is constructed in a different kind of materials for different kind of application, from general to sanitary, for beverage, for pharmaceutical industry. Standard would be in the material of stainless steel 316, but it is also, we can also supply in titanium, especially for desalination industry where the water is seawater. So again, it's monitoring the bacteria biofilm formation. It's not a generic, it will not detect generic foulings. It's high sensitivity, which means that by 1%, it will give us a significant readings. It's completely digital, which means that it can be constructed just using a standard cabling method or wireless. And it's real time, which means that it's continuously can be read and then can be read on the per second basis, per minute basis, or even per hour, depending on the applications. Yeah, next. So we're going to, as Dr. Lau mentioned, we're going to look at one particular case study or applications. That is the application of this particular sensor for the monitoring of the biofilm inside a chiller HVAC system or aircon system. Singapore especially is a very hot and humid, have a hot and humid climate. So all of the buildings would have air cons, and a lot of the air cons will use cooling towers as part of their systems. But in this, as the cooling towers is used, the cooling towers water contains bacteria, contains minerals. But a lot of people would think that probably the biggest problems would be sealing inside the heat exchanger, which is typically corresponds to the calcium carbonate or hardness scales. But in actual fact, biofoulings is more problematic inside here, because the cooling tower again is operating in an open environment, and then it's operating at temperature that is good for bacteria growth. Actually, it's about 35, 36, 37 degrees Celsius. Biofoulings is actually almost 5 times more insulating than common hardness scale, which means it's going almost have the potential to impede 5 times more to exchanger, lowering the heat transfer efficiency of a chiller system. At the bottom table, you can see a different chiller capacity: 300, 500, 900, 1,000 to 200, 2,000. Sorry, refrigerant tonnage of different size of aircon system, building aircon system, and only if we have like 0.3 mm of biofilm start forming, it will cost about 20 on the 2000 RT. It will cost about 26,352 more on energy in comparison to a clean system. So the biofilm monitoring system does have can contribute to the energy efficiency of a building. Yeah. The next one. Yeah. Yeah, this is the actual reading itself. As I mentioned, it the biofilm sensor, Alluvial biofilm sensor, do give a continuous real-time reading. So it gives us the readings, and then when the first day, second, third day, as you can see, the biofilms is sort of like mostly controlled by the continuous dosing of the cooling tower with biocides. But on the third day, it starts to build up. And when it starts to build up, it starts to build up fast. And then on the fourth day, as we can monitor, so once the biofilm has built significantly, the operator actually institute like a shock dosing of chemicals. Then once the shock dosing of chemical, which in this case is chlorine, it caused the biofilm to be removed, and then it dropped down again. On the fourth day, after the shock dosing, it dropped down again, and then it just continually sort of like monitor, maintained by the continuous dose. And then, but by the fifth day, by the sixth day, it starts to build up again. So they institute another chlorine shock dosing for about 30 minutes. And then the biofilm will start be removed again. Is the trend start to going down. And then the continuous dosing start to maintain. But on the 10th day, it's going up again, and so on. So this is showing how actually this Alluvial biosensor is able to monitor the biofilm formation in the HVAC system. Because a lot of the times we actually take a sample from the body of the water. So by monitoring the bacteria in the water itself, by taking a sample from the cooling tower and a total plate count, total aerobic plate count, and then we try to correspond it to the biofilm. But as you can see, the continuous dosing to the body of the water to the cooling tower system probably can maintain the bacteria into an acceptable population. In this case, in Singapore, NEA actually an institute that we have to have total bacteria population less than 100,000 colony forming units per mil of water. Probably from that regards, the total bacteria, as long as it's less than 100,000, is okay from public point of view, and fulfill the NEA regulation. But in terms of biofilms formation, probably it's not very good to have it around be at 100,000 or less than 100,000. It has to be a lot less. So as you can see, the biofilms, despite of the continuous dosing, is still growing on the equipment. And then toward the 13 days, 14 days, 15 days, there's certain changes in the water of the cooling tower water. As you can see, even the continuous dosing is unable to maintain, and the biofilm is continues to grow. Okay, next one. So the second case that I'm going to share with you today is on the application of this particular sensor for desalinations. This particular desalination system, the SWRO using an ultrafiltration system as a pre-treatment. And then, so the Alluvial biosensor is installed first in the feed to the RO, and then second is at the concentrate, just to as a comparison and as a confirmation of signals. Next slide. Yep. So this is the reading that was that we got during the trials. As you can see, even though the system using an ultrafiltration system, biofilm still start to grow after some time. So this one is, we can see they're using a certain chemical, which is DBNPA, and some chlorous ions, basically chlorine mixed with some other chemicals to flatten its oxidizing impact to the membrane to remove the biofilms. So this is a great way to monitor the biofilm in the desalination environment, because as you probably aware, one of the problematic things in the desalinations is biofouling by bacteria or by microalgae. So this is a great way to monitor and the cleanings after the detection of the biofilm formation. The cleaning was done by the chemical online without stopping the RO. So before the problems get too large for the SWR. So for the system, they do like on inline cleanings and then remove the biofilm by these particular chemicals. This is close toward the end of my presentation. Next slide. So yeah, this is we just started in Singapore about 6 months ago in introducing this Alluvial biofilm sensor to the market, but has been quite widely used, especially in Europe. Next slide. So yes, again, we are open very much for collaboration with research labs, and then for any private companies that would like to try the biofilm sensor for their application, pertinent applications in their plants. So you can contact me through the email below, where if you have a chance for us to collaborate. Thank you very much. Thank you very much.
Okay, a big thanks to all our guest presenters. Thank you for sharing with us on this interesting topic. And now we come to the Q&A segment. We limit to one question for each presenter due to time constraint. The rest will be answered and sent by email along with the presenter slides later. Okay, we have the first question, and it is for Professor Stefan. Prof, the question is, SCELSE involved in COVID-related research in the water system or air?
Thank you. Yes. So SCELSE is part of surveillance in both the water system, the water cycle, and in the air. That's become sort of part of a task force, a larger task force in Singapore, where SCELSE is contributing that skill of detection. And sometimes there's very low biomass and low biomass samples that needs to be analyzed. So yeah, the short answer is yes, we are indeed part of that.
Thank you, Professor. Okay, we have a question for Dr. Lau. Dr. Lau,
Yes.
can biofilms be formed under high potential fouling conditions, in bracket high COD or TOC levels, and even with sufficient biocide being introduced?
Yes, it can definitely form. Is that your question? Can it be formed under high?
Yes,
COD
can
level?
biofilms be formed under high potential fouling conditions?
Yes, definitely. It does form under high potential fouling conditions. In fact, COD serves as organics and food that would encourage the formation of biofilm.
Okay, followed by then, even with sufficient biocide being introduced?
With it depends on the type of biocide, really. Biocides could delay. Definitely, it would certain biocides would be effective in dispersing or delaying the formation of biofilm.
Okay.
But as I mentioned, there is a potential of introducing or encouraging the growth of resistant biofilm if you use the biocide repeatedly in a long period of time. So really depends on what type of biocides you're talking about, and hence yeah, it needs to be tested.
Sure, I understand. Okay, thank you, Dr. Law. Okay, we have one question for Dr. Amit. Doctor, the question is, with Biopsin's platform, what lead time are you aiming for?
So we are aiming to, from sample to result, that time we are aiming for to be less than 1 hour, less than 60 minutes.
Okay. Okay, yeah, there's one last question, and that's for Mr. Andy. Mr. Andy, regarding LVM, right? Regarding LVM biofilm monitoring, I should explain how does electromagnetic reflect the activity of biofilm activity?
This one is a very highly technical question.
So probably just overall, just a short explanation. Probably we can get back to this in more detail and give it a context. Maybe just a very brief explanation will do.
What I can understand from the founder itself is basically the biofilms, when there is a biofilm formation on the surface, they will start to react with the oxygens, and then in the water, then it will give out some electrons. The more biofilms forming on the and the more electrons will be released by the biofilm itself, by the bacteria inside the biofilm. So the electrochemical signals of the amount of electron is the one that get picked up by the sensor.
Okay. Okay, thank you, Andy. Okay, the one last question, back to Dr. Lau. It just came in, the question just came in. Okay, it's from Mr. Sabro, I believe. Okay, it says we work with high redox, in bracket ORP over 750 milliwatts volts. How effective is this product by eliminating biofilm with this high redox water? Dr. Lau?
When you say high redox water, when you say high redox water, is that again, redox is a measure of reducing agent and oxidizing agent. It again comes down to what exactly are the reducing and oxidizing agent in the water. Okay. So again, requires more specific information, which I can take it offline for discussions for sure, if the person is interested.
Sure. It's from Sabro. It's called hydrochloride active chloride. Yeah, it's in the
hypochlorite active chloride.
Yeah, correct. So yeah, Dr. Lau, probably you want to you can take this offline and contact Mr. Sabro. Yeah, sure.
Yes,
no worries.
Definitely. Yeah, happy to discuss.
Thank you. Okay, once again, thank you to all speakers on answering the questions. Any participants have further questions, do email to SWA. We look forward to seeing you again in our next webinar on the 27th August at 4 p.m. And the topic is on fostering water technology partnership. This journey organized by SWA and EWTCOI of Nanyang Polytechnic. Okay, thank you all once again for your participation and support in this webinar. Please continue to stay safe in these difficult times. Goodbye. Thank you.